Once again, I want to welcome you to Multivariate Statistics class. Um, I think before now, I've introduced you to what I call statistical inference with single vector, with single mean. But I also walk you through two sample multivariate version. Okay, so and that is where we left off. Um, I want to go into, I want to start from where we stopped. If you take a look at this situation where we actually have two groups, we want to compare two groups, and for each group, uh, there is this vector mean. There's a vector mean for this group, and there's a vector mean for another group. And probably you want to compare whether the vector means are the same or not. Um, we are borrowing an idea from univariate statistics, where when we want to compare two independent means from two independent groups, what we have an assumption. Assumption going forward is whether the population variances are equal or not. Okay. When the population variances are equal from univariate perspective, you actually going to use the test statistic that has to do with pool variance. Now I believe you've heard about pool variance before. Has anyone heard about pool variance before? Okay. Now, how do we extend this to multivariate situation? Okay. Now, in a multivariate situation, the difference between the univariate and multivariate is that, oh, I'm still comparing two groups. Okay. But in univariate, we're only focusing on one variable, but in multivariate, we're focusing on, more than one variable. Particularly if I actually want to compare the performance of two different schools, the performance of two different schools in probably in three subjects. The three subjects I talk about is what make it multivariate. Okay, maybe I want to look at the performance. We're not comparing separately. We are having a joint comparison where we want to compare simultaneously the performance of the two schools in algebra, in calculus, in statistics. So the question is, uh, for us to be able to know the approach of multivariate tests that we're going to use, we need to first ask our question, do the two groups have the same population covariance structure? I'm going to say that again. That is similar to the question that we normally have if you want to do for univariate, for two independent samples where you're going to say, do the two groups have the same population variance? But right now, we're going to ask ourselves, do they have the same population covariance? If they do, okay, if they do, okay, so what we're going to, what is actually going to happen is that we're actually going to use idea of a pool. If you take a look at this guy now, okay, SP, okay, it's what we call a pooled covariance structure. Now we take a look at the S1. The X1 and the X2 that you see here, they are the sample covariances. X1 is the sample covariance for the first group. S2 is the sample covariance for the second group. So we are pulling them. Okay. Now, if you take a look at what I have right now, okay, what will now be the test statistic after the pooling? Okay, what will be the test statistics after the pooling? Okay, the test statistics is this. Please, I need you to pay attention. Okay, take a look at this guy. Do you see this guy? Right? This guy here. Do you see this guy? It's what we computed from here. Do you see that? That P is what we computed. Okay. Now, if you take a look at this guy, that is a sample mean vector from the first group, maybe the average of a particular school in algebra, in calculus, and in statistics. And this guy is the average of another school, in the same subjects. Okay, so take a look at that. So that is a bottom line. Let me do this. I think I will share that again. I just wanted to make sense. Um, okay, that's it's gonna make a lot of sense. So let me share it to those who are online. Okay, so uh, like I said, the test statistic for that is what I show. 1 second. Okay, so this is the test statistic for that. What is this testing? It's actually testing whether there's a statistical significance in the joint performance of the schools in those subjects, not just one subject. Now, we also we need a distribution for the test, okay? Because in case you want to make use of a p-value, we expect that the test statistic should follow F distribution, okay? The test statistic, the Ottolenghi square now, will follow F distribution. Now, I just wanted to see that. Now, the next thing that I actually want to talk about is how do we also, if I'm interested in constructing confidence interval, let me tell you this. When you conduct when you conduct hypothesis testing, that is incomplete. Your research is incomplete if you do not construct confidence interval. Just like what I told you the other time, the hypothesis testing, we only test about how significance is an effect. And how significance is an effect does not necessarily translate into how large is the effect, does not translate into practical significance. And that is the reason why the moment you conduct statistical significant tests, you need to complement that with confidence interval. You know what this guy is telling me now? Okay, if I need a confidence interval, I actually want to guarantee, I want to guarantee simultaneous coverage, for all the parameters involved. So this is trying to say the probability of the Ottolenghi square less or equal to that critical value should be equal to a certain level of confidence. 1 minus alpha is a level of confidence. Alpha itself is a level of statistical significance. What do I mean by level of statistical significance? It means the maximum probability of committing type 1 error. The maximum probability of committing type 1 error is actually alpha. So 1 minus alpha will be level of confidence. So what will now be the formula now? What is going to be the formula if that coverage, simultaneous coverage is guaranteed? Okay. I'm actually before showing you the code, let me see. Okay, can you see the formula here? Okay, this is the confidence. This is the formula that we're actually going to use. But you know what? I need you to pay attention to this. What is that? That is still that pool covariance. The pool covariance will reflect in both test statistic and in the confidence interval formula. But you know what? How do you do this in R? Okay. How do you do this in R? I'm actually going to walk us through how we do this in R. Okay. I will advise you to run this code. Okay. Now, uh, let me walk you through this. Please pay attention. I just wanted to say this. Do you know what this guy is telling me? I want to perform a multivariate independent sample t-square, for situation where we got two populations and the two populations are independent. Okay. Now, you know what I'm trying to say here. Okay, I'm trying to say paired is equal to false. You know what I mean? I'm trying to tell R I'm not interested in dependent samples. I'm only interested in the independence. Does that make sense? And that's why you say paired equal to false. When paired equal to true, then it means I'm interested in dependent samples. Okay, the one that involve a repeated measure. But this guy now does not require that. So now another thing that I also want you to pay attention to, asymptotic force. Please pay attention. I remember when I was walking you through the one group, we talk about asymptotic test. I will also talk about exact test. Okay, the finite exact test. The finite exact test of the utility square only appropriate when you're talking about small sample. But when large sample is involved, we exact test is not appropriate. We're gonna go with asymptotic. Okay, don't forget that. So here, actually said, uh, you know, asymptotic equal to false. When asymptotic equal to false, it means the what I want to conduct here, the kind of test here is the exact test. Does that make sense? Of the alternative square. I created, okay? So and so on like that. So these are the code, that I'm actually talking about. But you know what? Let's see something here. Can we have a way to apply if I have a real life data set? Okay, I actually have a real life data set. In this real life data set, we got four major variables, okay, for whatever group. Do you see the four major variables? MPG, DIS, PHP, and WT. Okay, now, please, I need you to pay attention. Okay, please pay attention. I just want you to see what we're doing here. Now, we got this X4, X6, X8. We're talking about a vehicle that has four cylinder, a vehicle with six cylinder, a vehicle with eight cylinder. Whether four-cylinder vehicle, six-cylinder vehicle, eight-cylinder vehicle, they have four variables in each of that we measured. They measure the mile per gallon, okay, and so on like that for each of that. But what is the focus here? What is our intention? Can we have a way to compare if on average this guy they are the same in two groups? When I say two groups here, maybe I want to talk about between four-cylinder engine and six-cylinder engine. Okay, we want to compare whether the average simultaneously, whether the average MPG, DISP, HP, WT are the same. Okay, that is what this test is about. That what is what this guy is about. Please pay attention. If you don't understand, ask me question. Now, when I use that big formula that I showed you the other time, the formula on the t squared, it gave me this 39 point something. That big formula. Okay. Now the F starts, it actually gave me that. Decide the degree of freedom. They're going to be two different degree of freedom. The first degree of freedom is actually going to talk about the numbers of variables. We got four variables, and that's why the first degree of freedom equal to 4. And the second degree of freedom is necessarily going to be n minus p, the number of observation minus the numbers of features. And if you take a look at in the end, okay, when you see asymptotic force means I'm not running asymptotic test version of a t-squared. I'm only interested in the finite exact. Okay, and the finite exact is only appropriate when I'm dealing with a small sample. Does that make sense? Now, let's take a look at the p-value. You know what this p-value is telling you now, okay? Between four-cylinder engine and eight-cylinder engine, there's a statistical significant difference between the two mean vectors. Is there any question on that? Okay, now if you understand that, we can also compare take a look at this guy, compare between six-cylinder engine and eight-cylinder engine, and this one also compare between four-cylinder engine and eight-cylinder engine. We can only compare two groups at a time because we're talking about independent two groups. Does that make sense? Okay. And of course, using the p-value, you can take a decision in all. And using, if you take a look at this, where you have asymptotic force, means we are not conducting asymptotic tests. Okay. We are only conducting finite exact F tests. Is there any question here? Go ahead. To be able to answer that question, I will take you. That's a good question. Okay. Now, it should be n minus p, but I just want you to see. Let me see. Oh, sorry, for two groups. Now, is this, it's not n minus p. You see why I say I want to show you? The first one is this, p, number of features. The second degree of freedom is actually this, which is going to be the one of n minus p should be when I'm focusing on just one group. The one we did, today's Wednesday, right? The one we did on Monday. Okay. But because two groups are involved, then it's going to be, oh, the number of sample in the first group is n1. The number of sample in the second group, then I will subtract the numbers of variables. Then I will also subtract one. Have I answered the question now? Okay. Because what if in the exam, and I ask you to compute this, you should be able to know what a particular formula represents. So thank you for that question. Like I said, please ask questions. Okay. Now, now you now understand the degree of freedom, what each of these actually represent. You know where I'm going now. Please pay attention. What have I used the other time? The other time here, um, oh, wait a minute. That's too sensitive. Now, here, I use, I did not use asymptotic in any of these three. 1 second. Okay, so if you take a look at any of these three, asymptotic is false. But what if in a situation can we have a way to compare a finite test like this of Otterlin square for two independent groups in multivariate? Can we compare that to asymptotic one? And let's see what we're going to get. Just pay attention. That's what we want to do here. Look at it. Comparing finite sample. When I say finite sample, I'm actually focusing on small samples. With large sample is asymptotic. Does that make sense? Okay, now, but this time around, you know what I'm doing? I'm simulating data. You know what I want to do here? I only want to investigate sampling property. You remember when we're dealing with the one group, we investigated sampling property. We actually want to see how our test would behave, okay, how the asymptotic and the finite one would behave when we increase sample size. Okay, we did that for one group. We also want to investigate that property for two groups. Now, what was the conclusion for one group? The conclusion for one group is when the data set is small, okay, you conducting an asymptotic test, you may mislead. Okay, you can't trust the p-value because asymptotic test is not meant for small sample, but meant for large sample. But when you are now increasing the sample size, when the sample size is increasing, we expect the two tests to converge to the p-value. But you know what we want to do here again? We've already seen that for one group. We now want to see whether it remained the same for two groups. Do you want to ask a question? Oh, okay. When I saw your hands up. Okay, now, if you take a look at this, I simulated data for sample size 10, okay, and for four variables, okay. Now, oh my God, if you take a look at that, I'm simulating for two different groups. The first one is for the first group, creating data, simulating data for the first group. In the first group, there are four variables. In the second group, we also have four variables. Okay, so this is a simulation. Okay, even though if you have a real life data set, you can also do the same. Okay, but you know what? For us to be able to have some kind of understanding of sampling properly, we simulate because with simulation we can actually maneuver things. Now, take a look at this. This is the result. If you take a look at this, false, that is the finite one. True, that is the asymptotic one. This is what you're going to compare. Look at that. There's a large difference between the two p-values. Now, when I continue my simulation to moderate, okay, when I continue that to moderate, I just wanted to take a look at this. Okay, when I go all the way to 50, okay, you look at the p-value, they're getting closer now, right? They're getting closer now. Then when I get all the way to 100, you see they as a marginal difference. So what is the takeaway from here? The takeaway from here is our observation is actually the same. Okay, it's actually the same. Oh, can you give me 1 second? There's an urgent thing that I just quickly have to reply to. If you're not enjoying my class, please let me know because I want you to enjoy my class. Okay, thank you so much. Now, that is the takeaway. Now, I want to move right now. That is a confidence interval. I've shown you the significant test. Okay. Now, this is the code. Please make sure you run this code. Okay. Now, if this is where you want to apply that now to real life data. 1 second. If you want to apply that to real life data, this is becoming more sensitive. Let me quickly take you there. We've done that. Okay, so when you want to apply that to real life data, so what do we want to do here? We want to create a confidence interval. I just walk you through when you want to conduct. So I'm going back to the real life data on empty cows that we've used on cylinders. Okay, please pay attention. Now, this is going to give you here. I just want you to see this. What is the meaning of this guy? Okay, you're actually going to have average for one group and for the second group. Okay, now, this guy now, if you take a look at this guy, right, you can see here for N4 and N6 for two different groups. Okay, you can actually talk about the lower bound and the upper bound. when this include negative or includes zero, there is no statistical significance. Okay? But now, does it if you take a look at that, it look like that includes zero, right? Because of the negative. Can you see the negative? So there's no statistical significance between that and that. That's what I mean. So here, negative, negative, there is statistical significance. When you have negative, negative, positive, positive, of course, there's statistical significance. But when you have from negative to positive, there is no statistical significance. So you can see now, this is giving you for each of the group you are comparing. Okay? Like I said, your p-value is not enough. You also need to construct the confidence interval. Now, I quickly want to move. Let me tell you this. We don't just do what we do without reason why we do what we do. Before I'm actually going to use an Ottolini square that have a pool covariance structure, I'm going to say that again. Before using Ottolini squared with pooled covariance structure, I need to first run a test. What test is that? I'm actually going to call that test a test of homoscedasticity. I want to see whether the two population group have the two group have the same population covariance structure. And that is what this is talking about. We call that heterogeneous covariances. Because situation where the covariances are the same, the formula that I'm actually going to use will reflect a pooled covariance structure. But what of in a situation where the covariances are not the same? I can no longer use the formula that have a pool covariance structure. Does that make sense? And that's what I want to do here. So that's exactly what I'm doing here. Now, situation where they are not the same, oh my God. I just wanted to see a new brand formula. When now we're not going to use the T square that has to do with the pool covariance anymore, but we're only going to use the one that has to do with the individual. Take a look at, do you see any pool covariance in this formula again? Do you see that? We don't see that. SP is disappeared. We don't need it. We only need a pool covariance structure when there's an assumption or we verify that the population covariance matrices are the same. When they are not the same, this is what we're going to use. Okay, that is what we're going to use. Okay, now I actually moving now. I'm actually moving now. Okay, give me 1 second. I'm actually moving now. Now, uh, I will quickly walk you through. Now, what will be the situation where the covariances are not the same, and I use this. What will now be the distribution of the test? The other time, the distribution has been F distribution, right? Now, but now when the covariances are not the same, okay, it's still going to be F, but with different degree of freedom. Please pay attention. Pay attention. Okay. Now, can somebody look into this? You remember the other time? Can you hear me? Excuse me? Hello? Yeah, can you hear me? You remember the other time you asked a question, right? That has to do with what is the second degree of freedom, right? Now, the second degree of freedom, then when the population covariance are the same, I think it was N1 plus N2 minus P minus 1. But when the population covariances are not the same, the second degree of freedom will change. Look at that. The first degree of freedom is CP, but the second degree of freedom is V minus P plus 1. But you know what? That very V need to be computed. Oh my God. Look at the V. Look at what you're going to do to get the V. It's getting complicated. The V that I need, that I'm going to say V minus P plus 1, that V has to be computed from this. What is P? P plus P square. Of course, P is the numbers of variables. Uh, what is SK? Okay. The SK is actually going to be talking about a particular the covariance structure. But you know what? And if SK is the covariance structure for a population K, what is S0? The S0 here. S0, this is how I'm going to get S0. S0 is going to be combining the sample covariance of the first group and the second group. Please pay attention here. This is very, very crucial. Okay, now I'm actually moving right now. I'm actually moving right now. Now I want to move right now. This is the code. Please read the code. Okay. Now, and I actually repeated this. I repeated this again now. I'm assuming. Now, I just wanted to see something now. Can you see something now? I'm going to show you something now. Are you ready to see it? Take a look at this. Mm, mm. I'm going back to the engine, the same data. And you know what I want to do? What is the name of the test? The conventional, the exact test, asymptotic force. But I want to have generate two different set situation where population variances are the same and situation where population variances are not the same. That's why you see variance equal true. Where you see variance equal true means, okay, I'm using the formula, okay, when the pool variance is involved. Now, where the variance equal false, I'm using the second variant, the second formula that I just show you right now. Does that make sense to everyone? Okay, now you can compare the p-value. Okay, look at the p-value here and look at the p-value here for the real data set. Okay, now I needed to pay attention. Okay, this is for the simulated one. The one that you're seeing here is actually for the simulated one. Okay, I simulated. Look at that. I simulated data for two different groups. They have four different variables. Okay, they have four different variables. And of course, I'm actually comparing two different utility square formula. But the utility square formula that I'm actually comparing here, they are the finite utility square, not the asymptotic one. But I'm comparing two different one that assume equality of covariances and the one that assume, that they are not, the covariances are not the same. I'm done. That is the end of that. Now I quickly want to move. Let me tell you this. What have we done so far? We've been able to, we've considered one group. We conducted inference on one group. We considered two groups. We just finished two groups now, right? We actually had statistical inference on two groups, and I show you different kind of stories. But you know where we're going right now? Okay, we've done one group, we've done two groups. What if in a situation where we have more than two groups? Then that will take us to analysis of variance. Okay, now you remember now I want to quickly walk you through something because you're actually going to flow now because we're building on something. You understand how we do one group. You understand how we do two group. When we started one group, we started with the univariate. We generalize that, we extend that to multivariate. Okay. When we started two groups, we started with the conventional univariate, okay, for two groups. I walk you through PET test, I walk you through independent one, and we generalize that to multivariate. But you know what we want to do right now? What we want to do right now is we want to talk about three groups, more than two groups, but we want to start the building from the univariate version, okay? Then from there, we're going to extend all the way to multivariate version, okay? Because of that, I want to welcome you to analysis of variance. Analysis of variance, I'm going to start with the univariate. Okay, now in analysis of we use analysis of variance when you want to compare means in more than two independent groups, which is a generalization of what we've been doing. If you're talking about we have different kind of analysis of variance. We have one way, we have two ways, we have three ways, we have factorial design and so on like that. But we want to focus on one way right now. I want to focus on one way. When I say one way, what do I mean by that? One way means I have one factor, one categorical factor. But one categorical factor with levels more than two. The levels more than two means the categories that we're talking about. Now, what is going to be the model? Okay, please pay attention. This is the model. Analysis, in the analysis of variance, this is going to be the gram mean. This is the treatment effect, and this is the error. Okay, now you have that in the conventional analysis of variance. And let me tell you this, the error I must follow normal distribution with the mean of 0 and the variance sigma squared. Now, what are the model parameters if I want to estimate? Of course, my estimate of the population mean will be sample mean. And of course, the treatment effect is actually the difference between the mean of a particular group and the overall mean. Okay, this guy is the estimate of the error. Estimate of the error. Take a look at that. Okay, and this is how if I want to get the overall mean, this is if I want to get the mean for a particular group. And of course, please pay attention now. What hypothesis are we testing in the analysis of variance? The hypothesis we are testing is that H naught, the treatment effect is 0. Against it is not. You know what I mean? When I say treatment effect equal to 0, it means there is no statistical significant difference between the means of the groups. Why the alternatives get there is. But let me tell you this. What is analysis of variance doing in the actual sense? Analysis of variance, partitioned the total sources of variation. This is the total sources of variation into different components. Please pay attention. Okay, analysis of variance will enable us to split or break down, okay, the total sources of variation into separate components. The first component is what we call variation between groups. Okay, and the second component is variation within a particular group. Okay, and you know what? The test, please pay attention. We're actually going to use F test. And you know what the F test is going to do? The F test is going to consider the ratio of between variation to the within variation. Okay, and we're going to have 2 degrees of freedom. Okay, let's see the fourth degree of freedom is going to be G minus 1, numbers of groups minus 1. The second degree of freedom is going to be number of observation minus the numbers of groups. I just wanted to take note of that. Okay, that's for the one group. That is univariate. But you know what? I want to extend this to multivariate. Initially, the outcome variable was just one variable. Okay, but right now the outcome variable is no longer going to be one variable, it's going to be more than one, and that's why we want to extend this to multivariate version. And you know what, if we are extending this to multivariate version, we expect the variable to follow multivariate normal distribution. This is still going to be the model. Take a look at that. But uh, the error in the model now will follow multivariate normal. Okay, can you see that? Multivariate normal. Okay. Every other thing still remain the same, except that all of this will be in a matrix form. Why are they in a matrix form? They are in a matrix form because of the fact that more than one variable is involved. We're also going to have a decomposition. You remember at the time? Analysis of variance enable us to decompose variation around a response into, between, and within. It's also going to enable us to do so when more than one variables are involved. But when more than one variable are involved, we're going to call that cross-product decomposition. So take a look at this. This is the sum of square total, okay, which is the total sources of variation broken down into that and that. Okay, but I just wanted to pay attention. Okay, the within. I'm actually going to call the within variation matrix W, matrix W, okay? And, mathematically speaking, this guy here, everything here is the same thing as this guy. You know what that guy mean? The second one? Oh my God. I'm actually going to have the covariance for each group, okay? Then NK will be, what is the number of observation in each group? Take a look at that. That is a weighted. That's a W right now. Okay. And of course, SK is the covariance. You know how to get the covariance, right? Please pay attention. Now, it's going to take me to MANOVA table. In the case of univariate, we call that ANOVA table, but this is going to be a MANOVA. The M is the multivariate that we'll talk about. Now, oh my God, look at that. The B, we're going to have a matrix B, that will be between. We're going to have a matrix W, that will be for within. We're going to have a total, which is going to be B plus W. Okay, and we have the degree of freedom. And let's take a look at the F test. Oh, can you see the F test? The test here is going to be this guy, where is going to be the ratio of the generalized variance, that is the determinant of within, divided by the determinant of the total. Take a look at that. And we're going to call that wiki lambda. Okay, that's a wiki lambda test. Okay, that's a wiki lambda test. And let me tell you this. I now need you to pay attention now. I need you to pay attention now. What will be the distribution of the test? The distribution of the test depends on P and G. It depends on the numbers of variables and the numbers of groups. When you have one variable, when you have univariate, okay, and you are comparing from two groups and above, it will follow F distribution. Look at that. With degree of freedom G minus 1 and then minus G. Okay. When it is P equal to 2 and that. So you can see they all follow F distribution, but with different degree of freedom. Okay. Depending on the values of P and G. And situation where sample size is large, it will follow chi-square. Look at that here. If sample size is large, it's going to follow chi-squared. You know, everything's centered on wiki lambda. This guy is wiki lambda. The wiki lambda, you can see in each of these, having wiki lambda, where is wiki lambda coming from? This is the wiki lambda, the ratio of that. Please pay attention. Okay. So now we also have others. We have other maneuver tests apart from the wiki lambda. We have a lolly, or telling trace, pillar trace, and so on. But all of them actually rely on the matrix B and W. But before I go today, let me show you this. This is one way maneuver in R. Okay, and I conducted all the tests, different kind of tests, pillar, and look at the p value. Okay, you reject the H naught in all categories. Take a look at that. Okay, you can go through that. I'm actually going to start. I like slowing down. So it's not a matter of quantity, but it's a matter of quality. Okay, so I'm going to start from here on Friday. What are we going to do on Friday? We're going to look at the variance of treatment effects. We're also going to look at when I have more than one factor. What we just did right now. If I have just one categorical factor, that's why it's called one way. What if I have two categorical factor? I have a factor A, factor B. This one has levels. This one also have levels. Then I'm going to be calling that two-way multivariate analysis of variance. So this is where I'm actually going to stop today. And by tomorrow, okay, check the canvas for exam results. But you know what I've seen so far? You're doing good. But I want you to do more. Great. I want excellence. But you try. But by the time you see your results, you're gonna know what you're going to improve upon. That's what I got. Stay safe. Have a lovely day. See you on Friday.